In this video here, we're going to take a look at equilibrium. So if a rigid body is in equilibrium, the resultant force in any direction is 0 newtons. The resultant moment about any point is 0 newton meters. And then finally here, the sum of the magnitudes of the clockwise moments are equal to the sum of the magnitudes of the anti-clockwise moments. So basically for the last point here, all we're saying then is the clockwise moments are equal to the anti-clockwise moments. So 3 points here. That's all we really need for an introduction to equilibrium. I think the best way to demonstrate this concept of equilibrium and these 3 points here is to run through a couple of practice questions. So let's get started then with question 1. So let's get started here then with question 1. So for question 1 here, as we can see, right, we have this diagram. And this diagram here shows a uniform rod AB of length 5 meters and weight 30 newtons that is resting horizontally on 2 supports X and Y here. The question then asks us to find the magnitude of the reactions at X and Y here. So to begin with then, let's just go back to the diagram here because we are missing a few forces. So obviously we're missing the reactions at X and Y here. Let's just quickly add those to our diagram. So let's say that this here then is the reaction at X, which I'm going to label as R subscript X here. And we also have the reaction at Y, which we'll label as R subscript Y here, like so. And we also have the weight of the uniform rod here. So because it's a uniform rod, right, the center of mass is at the midpoint. So we have a total length of 5 meters. That means the center of mass is at 2.5 meters. So let's say that this is here then, like so. That's the weight here then of 30 newtons. Okay, like so. And we've now got everything that we need here then to find the magnitude of the reactions at X and Y here. So to get us started here, then let's just begin by resolving vertically. So if we resolve vertically here, right, like so, then in this case here, the forces acting upwards are equal to the forces acting downwards. So what I get here then, nice and straightforward, is Rx plus Ry is equal to 30 here. Okay. And what we're now going to do next here is begin to take moments. So we need to choose a point to take moments about. So for this example here, I'm going to choose to take moments about X, but it doesn't actually matter, right? We could choose to take moments about Y, and that's absolutely fine. Generally speaking, you want to pick the point which produces the least amount of algebra, but for this example here, it doesn't really matter. So choosing to take moments about X here, what we need then is the clockwise moments and the anti-clockwise moments, because later on, we're going to equate those. Okay. So let's begin then with the clockwise moments here, which in this case is nice and straightforward because imagine you hold the rod here at X, right? I now need to consider what force here would produce a clockwise moment, which in this case here is just this force of 30 newtons acting downwards, right? If I was to push downwards and I'm holding the rod at X here, the rod would start to go clockwise, okay? So the perpendicular distance here, that's this distance here, would simply be 1.5, right? So 1.5 meters here, like so. I've got 1.5 times by the magnitude of the force, which is 30. So 1.5 times by 30 here. If we evaluate that, we get 45. So that's the clockwise moment here. And now we also need the anti-clockwise moment. Okay, so using this arrow here to represent the anti-clockwise moment. So for the anti-clockwise moment here, that would be this force here. So in that case then, the perpendicular distance here is 2, or 2 meters I should say. So 2 times by the magnitude of the force, which is Ry. We get 2 lots of Ry here, like so. Just write it like that as well. So now what we're going to do here is equate the clockwise moments and the anti-clockwise moments. So clockwise is equal to anti-clockwise here. If we do that now underneath here, what I get then is 2 lots of Ry is equal to 45 here. Okay. And obviously what we want now is just Ry, so divide both sides by 2 here. And what I get then is Ry is equal to 45 over 2, which gives us 22.5 here. Okay. That would be 22.5 newtons there. Now don't forget, we do also need the magnitude of the reaction at x here. So to obtain the magnitude of the reaction at x, we just go back to the original equation here and just substitute Ry into this equation here. So Rx then plus Ry, which is 22.5. So plus 22.5 is equal to 30 here. Okay. Subtract 22.5 off both sides. And what we find then for Rx is we get 7.5 here. Okay. So 7.5 newtons there. And there we have it. So that gives us the solution there to question 1. And if we just take a look then at one more question here, we have question 2. So for question 2 then, as we can see here, right, we have this diagram. And this diagram here shows a light rod that is in equilibrium in a horizontal position under the action of a set of forces. The question then asks us to find the values of the unknown forces A and B here. So again, as you can see, right, pretty standard stuff. So to begin with then, what we're going to do here, just as we did for the previous question, we're going to begin by resolving vertically here. So by resolving vertically here, right, again, forces acting upwards are equal to forces acting downwards. So what I get here then is A plus B is equal to 5 plus 20. Okay, so that would be 25 there, like so. And what we're now going to do here is take moments. So again, we need to choose a point here to take moments about. Again, generally speaking, you want to pick the easiest point to take moments about, but for this example here, again, it shouldn't really matter. So if I take moments about A then, okay, if I take moments about A here, like so, what we need then is the clockwise moments and the anti-clockwise moments. So let's begin then with the clockwise moments here, like so. So this here then, this arrow represents the clockwise moments. So imagine you're holding the rod up at A here, right? And what forces here would produce a clockwise moment? So that would be this force here, right? If I was to push downwards here, the rod would go clockwise. And same again here, if we were to push downwards, again, the rod would go clockwise. So that's going to be these two forces here. So perpendicular distance is a meter. So 1 meter, or just 1, times by the magnitude of the force, which is 5. Get 1 times by 5. Put that in a bracket here. I also need the second moment here then, which is going to be 3 because it's the perpendicular distance here. So that's 1 plus 2. So I get 3 times by the magnitude of the force, which is 20. So 3 times by 20 here, like so. And if we evaluate this here, then what do I get? So 1 times by 5 is 5. 3 times by 20 is 60. So 5 plus 60 gives us 65 there. Okay. And now for the anti-clockwise moment here, using this arrow to represent the anti-clockwise moment then. In this case, that would be the single force here of B newtons. So if I was to push upwards here, right, the rod would start going anti-clockwise. So the perpendicular distance here is 1 plus 2 plus 1. So that's 4 times by the magnitude of the force, which is B. So I get 4B there. Okay. And what we now do here is equate the clockwise moments and the anti-clockwise moments. So clockwise is equal to anti-clockwise here. So in that case then, let's do that underneath. What I get here is 4B is equal to 65. And then just divide both sides by 4 here. And what we get then is B is equal to 65 over 4. And that gives us 16.25 there. Okay. So that's the magnitude of this unknown force B here. But we do also need to find A. So again, just refer back to the original equation here. That's this equation here. So in that case, then A plus B is equal to 25, but we do know the value of B here. So A plus 16.25 is equal to 25 here. Now just subtract 16.25 off both sides. And what we find then for A here is we get 8.75. Okay, so A is equal to 8.75 there. Okay, so B, 16.25. I'll also add on the units here, just ask for the value, but I'll add the units on just to be precise. So 16.25 newtons there, and same again for A here. Okay, and there we have it. So that gives us the values of the unknown forces A and B. And that actually gives us the solution to the very last question here, question 2. And that brings us to the end then of this video here on equilibrium.